the reason why we want to remove trends, basically, say, well, we want to get just to the meat, like kind of like what's left after we take out all the things that we can explain with time. Okay. So, like I said, here is our goal is to make the time series stationary. Basically, we want to make it so that the way I like to imagine this is that like there's no new dependence in time. All of it's kind of like the pure, just like function versus like the time dependence. The most common reasons for non-stationary series are things like seasonality, so there's a periodicity, right? Or a trend where it's like going upward or exponential or whatnot. Okay. So, oops, I kind of made it smaller, but that's fine. We'll kind of zoom right through it. So quick check, why do we want to get a stationary, right? The way I kind of see this is like, it's a way for us to get rid of the temporal dependence. We just have the noise left. And that noise is, what's causing that noise? If I were to say like, oh, all we have is the noise that's left, what are things that are causing this like quote unquote noise? You gotta guess, like just in general. So just say like, let's say go back to our stock market, right? And you can see like there doesn't seem to be a specific trend, like maybe you can find some, but let's just assume there's not like any real trend that we can find. This is kind of noisy, right? It's not like a flat line, right, of this adjustment. What are some causes of possibly the stock market going up and down?
Economic cycles.
Economic cycles. The CEO said, oh, go ahead, Tara.
Like news events or
news events, yeah, good. Yeah, maybe a product was just announced. Maybe the CEO was caught using another product in front of people and the stock went down for some reason. Some other political thing happened, you know, someone sneezed a little bit too hard or something one day. Like, I mean, there's just so many different aspects, right, to that, that fluctuation. But that's the point, that's the noise. We want to say, okay, well, the rest of it now, can we explain it? And we'll see something similar. I think we'll actually look at the one with the miles going forward. So that noise can basically be modeled based on other features. And we think of like stationary as like independence. So like you can think like, you know, once we get to stationary, it's like, okay, it's independent of time now. It's not specifically tied to the time itself, where we might have something like, oh, it increases over time, or there's a period, like a seasonality to it. Okay.
Victor, can you say more about the noise can be modeled based on other features? I don't understand what that means.
Yeah, so let's say, for example, you suddenly see, I'm trying not to use the example we're going to use. So say you see the stock market all of a sudden like dip down out of somewhere else. Well, that might be because there was some other, let's say like, that might not be the best example. I'm trying to think of a good example of this. It's not going to be like too crazy, but all right, I'm just going to use the one that we're going to look at. We're going to look at our number of miles flown over time. And we'll see that, as we saw from up here, is that there seems to be some seasonality to it, right? And then there's others seems to be going up, right? And then kind of maybe comes down a little bit. But we'll see, like, once we decompose and take out those trends from time, we'll actually see there's still some kind of like quote unquote noise. Like, that's the way I explain it. Noise might not be the best way to explain it, but essentially there's going to be something else there. And we'll see like in the 1960s, like there's almost like no real change that's tied to like time dependence. And you're like, there doesn't seem to be that many people flying out of normal. Like, what was going on there? It's like maybe people, for example, I think when I had another cohort do this, I said like maybe it's the Cold War. It's going down the 1960s. And so you don't see much of a change in that. And that's the other features I'm talking about, things that are not directly related to time. So if you think about this time series right here, all we're looking at is number of miles flown and what time of the year it was. That's all we're looking at. So if we can basically remove all this and say, okay, well, we didn't consider any other features, essentially that's what our stationary model can be looked at. Does that make sense?
Yeah, I think so. I think I'm just used to like hearing about noise as being sort of like natural variation or like random. Yeah. So I guess it just confuses me that is something that could be correlated with the dependent variable, right? It's not just like random.
Yeah, noise is probably not the best word for it. I think that's kind of like coming from my side, is that like I think of noise as being like there's something that causes it. So it really shouldn't be called noise. It really should be just like, oh, other fluctuations from as a flat line.
Okay, yeah, that's helpful. Thanks.
So, all right, I'll move on then to say, okay, let's go and start removing trends, right? So the first one is a log transformation, which is like, I think like it's always like a really nice one to use in general, like you've seen like probably in the first project. You can use a log transformation to basically punish really large values. Basically, it helps us to, first of all, if there's not a linear trend, we can make it linear, right? By making using log is the opposite of exponential. And also we can make sure that there's a certain heteroscedasticity, right? So if you have a lot of variance across it, you basically can squish down those larger values to make it more, what's it called? That less variance over time and everything. So this helps us, remove that trend here. So kind of like showing you some examples here. Basically, I'm going to show you, it looks like that time series that I created to begin with, using with no transformation, a log transformation, right? And then also use a square root transformation. Note that I put here, you can use square roots and cube roots to also do the transformation. Log transformations tend to be more common. This is technically like mathematically like the slowest growing function or monotonically growing function. So it's a really useful one to use, but sometimes you might see a square root transformation or you might just try to see if that works better. Okay, so I thought I'd throw it in there. So you can see here's our original model and you can see our log transformation here. Okay, you can see is that basically this makes it more like a log transformation, but you can see here is like when we look at this, it's a little heteroscedastic. There's a lot of like very little variance versus this big variance over here, right? So in this case, I tried doing a square root one, and you can see the square root one looks relatively linear. We still have some heteroscedasticity, but that might be okay, or maybe just that's just the nature of what is going on. Also, it's kind of subtle, but I think there's a slight, we didn't remove all of the exponentiality in this, right? It's not quite linear, but you might have to sacrifice between the two. Okay, but generally you'd use linear or a log transformation. Okay, cool. All right, so once we get it basically the more linear, we'll have a lot more easier time working with it. Because remember when we tried doing things like the rolling mean with a exponential trend, it was really tough to actually get something that like follow the model and look nice and clean, right? We saw that it always underperformed this large part. So if we have this now, it should hopefully follow closer to like this trend actually is going to be. So the rolling mean, basically, we have this value and we're going to subtract it off. So we get something that's closer, like getting off like essentially, the way I kind of think of this is like the reason why you have this increase over time is because you start off really high, right? And so the next one is going to be a little bit higher. And so it kind of keeps increasing. So we're subtracting off that mean. So basically we're kind of removing that trend upward. We're just kind of keeping it so it's flat. Okay, so let's go ahead and run this guy. So you can see here's my actual square root. So I did a square root in this case. I think this is kind of following the curriculum. I think they might have used a square root. But then we have our rolling mean. So you can see here in red, and you can see I used the window of 4, which is probably about right, what you'd want. And you can see here, it kind of follows along here. That it doesn't seem to underperform or overperform in any particular way. It's like a noise, and we're going to subtract that off. So essentially, we're going to take each point and subtract off this number. So essentially what we're going to look at is the distance from this rolling mean to the actual point that we had. Okay, so we do this now because what's nice is that these are both series, right? So we can just subtract the two, right? Also note though, however, this will produce some nans, right? So not a number, because this guy right here, we don't have a rolling mean. So if we do minus, nothing essentially, this is going to basically say, oh, that's not a number. So we're going to drop those nans. So essentially we're sacrificing this earlier stuff. That way we can make sure we have a full data set. Okay. So we have this, and now we can actually plot this out. So if things did really well, we should hopefully see not too much variation from the rolling mean itself. Okay, run this now. And you can see here, yeah, okay. And you can see that variation is relatively small. There's still some in here, right? But you can see there's no longer an upward trend, right? We're removing that overall upward. You can see more or less it's kind of scattered randomly across like 0, or at least a specific number. Maybe not 0, maybe like 0.1 or something like that. Okay, cool. Any questions on how I kind of created this rolling mean and then subtracting it out?
Okay, so just backing up a little bit, I understand the idea of subtracting the rolling mean so that you're sort of removing any kind of trend that's upward or downward, right? But can we just why are we removing the trend? Is it related to the temporal effects of time Like, is that another thing we're trying to get rid of to understand like, what else might be impacting?
Yeah, the way you can kind of think about this in some ways is by removing the trend, it means that you know what the trend is. And so we're trying to remove the parts off that we kind of can figure out and know to the stuff that we can't easily model with just time by itself.
So by removing, like, by subtracting the rolling mean, what are you, like, what trend are you removing that now you understand better?
We're removing that upward trend going forward. So like you can see here, it's basically there tends to be an increase of the mean, essentially, more and more and more. So we're basically subtracting off that increase, which is why we get something that's a little more flat.
Okay, because like that wouldn't be, because your like starting point the next year would be higher, so it's not exact. I think I understand what it's doing, but
yeah, and we'll actually we won't like really get rid of it when we do decomposition. We'll actually split it up into different parts. Like, okay, here's the upward trend, here's the seasonality, and here's the residuals.
okay.
So right now we're basically just we're just trying to get to the residuals.
Okay. Thanks.
No problem.
I guess to piggyback off of that, I mean, I guess I'm curious, why is it even useful to do that, to transform it and get rid of the, I guess, the time trend?
Yeah. Again, it's kind of more like if you can get rid of it, and this is like, in reality, we're not going to get rid of it. We'll see in the decomposition, we can actually separate out the trending. Oh, this is the upward trend part. Here's the seasonality. But in this kind of scenario, you can kind of think of like, oh, if we can remove it, it means we can explain it. If you're just kind of guessing and it's like you can't make a decent change, it's kind of like you don't actually understand it. Hopefully, it's like kind of like it's like a multiple choice answer where it's like you might not know the answer, but you know which ones are not the answer. It's kind of like you're getting rid of, oh, well, I know it's not this because I know this is not true kind of deal. Maybe not the best analogy here, but you can kind of think of like, oh, well, if we can remove that upward trend, then we can look at the things that are like, okay, what's not the upward trend or what's contributing to the value that's not this upward trend in the time series. Cool. Makes sense to people? Cool. All right. Maybe we'll revisit this too on decomposition. So maybe that will be a little helpful too, seeing like.
Is this? I haven't read the curriculum for this section at all yet, but is this like the opposite of like a random walk kind of?
Yeah, so actually this is section 31. So 32 is going to talk about random walk and stuff like that.
Yeah.
Yeah. So that's essentially what's going on here is that this would be kind of jumping into the future, right? Is that this will be closer to a random walk. This is something like a drifting walk. So a random walk with a drift. Essentially we're drifting upwards here. We're removing that drift. So we can get just the random walk itself.
Okay.
Okay, cool. All right, yeah, I think this will help when we start revisiting some of these parts as we go through. Okay, so I just wanted to show this part. Little quick note is that there's a weighted rolling mean as well. So note that sometimes you might have things that are like things matter more in a certain time period. So you might actually have like something like an exponential weighted mean where, excuse me, exponentially weighted moving average. So you can imagine like as you kind of, what's the word for it, is that instead of just making each point as important as the next, so if you have a window of like 4, each one of those 4 points are super important. Well, that might not necessarily be true. For example, let's say stock prices. The most recent one, like the stock price from yesterday is probably more relevant than the stock price from 5 days ago. So you might want to put more weight on that one from yesterday. So essentially that's what a weighted moving average is here. So you can think of like exponentially weighted moving averages. We're kind of giving it more weight to something maybe in the past. Okay, cool. So I just wanted to throw that out there. That option exists. Okay, and then so the last part for removing trends. So we can see this part. It's like, okay, we got this kind of funky looking trend right here. There's no upward part. We can do differencing. So differencing is basically taking off points from the previous one to essentially say like, well, okay, like the reason why, let's just pretend this a little bit, is that the reason why this point exists higher than the other one is because the point from prior. If you already have a high stock price, maybe that means that you're going to have a high stock price the next day. So we can use differencing to basically remove a pattern from there. And so note that the differencing, basically it depends on like what your period you're looking at. So in this case, if we look at just like one period right here, so I think we showed differences from last time. Okay, you can see here, it's like, okay, that didn't really change very much, or I mean, it looks like it made a little bit of difference of saying, okay, from the previous one. But let's say we try out something like 10, just to give you guys a feel for like what this difference is. And you can see here is that we're actually moving from the previous point. So we're actually saying, oh, a difference from 10 ago. It's like we're actually reintroducing, what's it called? I don't think actually, is this right? Yeah, we're reintroducing that part. Okay, so that would be the next step, is differencing. I think this is going to be a little more clear when we actually do decomposition. Something I'm going to kind of skip over this part unless you guys would like me to talk a little more about this differencing aspect. Okay, I think this is more clear with something like the temperature data. So I'm going to plot the temperature. I think it looks like I plot the temperature without any differencing, and then I'll go ahead and plot the temperature after doing a difference of 365. So you can see here is that this is the data, and I'll show this beforehand. So you can see here, this is the data, basically the temperature changes over a year, right? This is nothing's changed by itself. If I do a difference of 365 years, it's basically going to look at the past 365 and look at that difference from here. And you can see is that we're removing that periodicity, right? That seasonality. Essentially, we're saying, okay, well, we know at this time, 365 days ago, it's about the same temperature as before. So we're just saying, oh, what's that difference between those different points? Okay, note that we still have a lot of static heat, but we have a lot less difference in the, what's it called? In we're removing that that period essentially. Okay, cool. Does that make sense to people? Is that how we're basically lagging and saying, okay, like, well, how are you different from the previous point from 365 days ago? Cool. Kind of. Yeah, I think this would make more sense when we do decomposition. So let's try decomposition and see if you guys have more questions from here.